Hello, everyone, and welcome to this Science with QuEra webinar, a webinar series where we present scientific works by QuEra scientists and collaborators, sometimes the other way around. My name is Yuval. I'm Chief Commercial Officer of QuEra. And today we're going to talk about a Nature physics paper, constant overhead fault-tolerant quantum computation with reconfigurable atom arrays. I'll start by a brief introduction of QuEra and then hand it over to Pablo and Harry, the presenters and co-authors of this paper, to talk about it. I encourage everyone to submit questions as you have them in the chat or in the Q&A box, and I'll try to interleave as many of those as I can. Those that we're not able to answer in the webinar, we'll try to respond offline. So QuEra is a company that's located in Boston, partnering with Harvard and MIT. And in fact, we feel that the proximity to Harvard and MIT is one of our strategic advantages. We build quantum computers using neutral atoms. Many consider neutral atoms these days to be the workhorse of quantum computing, the most promising approach to large-scale fault-tolerant quantum computation. Our first computer, Aquila, has been on Amazon Web Services on Bracket since November of 22. And we're installing on-premises computers as well. I'll show you one in a bit. QuEra recently closed a $230 million investment round led by Google and SoftBank. So we're definitely here to stay. And we partner with enterprises, with HPC centers and governments. And we'd like to serve as sort of their innovation partner, assisting them in their quantum innovation journey. In my view, quantum computing journey or the quantum computing industry is progressing in 3 steps. You know, it was 10 years ago or so that people were asking themselves whether quantum computers could be built at all. Could you build something with 2 qubits and get them entangled? And then obviously the answer is yes. Many companies have demonstrated that to be the case. The next question was, can errors be corrected? Qubits are fragile, and if you cannot detect and correct errors, then you're limited in the length of the calculation and therefore in the usability of the calculation. And I think a watershed moment was in December of 23, where a paper by Harvard in collaboration with QuEra and MIT and NIST and University of Maryland showed 48 logical qubits, an algorithm of 48 logical qubits. And since then, both QuEra and others have also shown that errors could indeed be detected and corrected. And then the next question, which we're all working on right now, is can we scale this to truly useful quantum computers? And based on this progress, I and many others believe that truly useful quantum computers could be just 2 or 3 years away, and therefore organizations would do well to get started if they haven't done so already. So QuEra wishes to serve as quantum innovation partners to those that want to go into the quantum journey. And we do so in 3 ways. We deliver quantum systems either on-premise or through the cloud. We do collaborative research. Quantum error correction is one topic, hybrid algorithms and others. And we also do application co-design, which is working with customers to do full stack optimization to try to extract the maximum value of today's hardware and adapt it to the particular problem at hand. As I mentioned, our first generation 256 qubit Aquila analog computer is on Bracket. Until very recently, was the only publicly accessible quantum computer for 2.5 years. So we're very proud of that. It is available about 130 hours a week. So no excuse. You can just take out your credit card, or if you already have a Bracket account, you can use it this afternoon. We've seen plenty of people worldwide use it for fascinating applications, from simulation to machine learning and optimization. And that has also resulted in several exciting scientific publications, from string breaking to quantum reservoir computing to optimization and much more. We also build gate-based model quantum computers. Here's a picture of our quantum computer that's installed at the National Institute of Science and Technology, AIST, in Japan. It is fairly easy to install for an HPC center. No cryogenic cooling is required. It's very power efficient. And when we deliver it, we include on-premises installation, maintenance, application support. So everything you need to make the most out of the computer, integrated with classical infrastructure. And we see an increasing number of HPC, high-performance computing centers, that are looking to quantum as the next big computing modality. Speaking of which, we're partnering with Nvidia. Nvidia is opening what they call the NVAQC, the Accelerated Quantum Research Center in Boston, not far from QuEra. And we're working with them on optimizing classical quantum integration, whether it is for error correction, for hybrid applications, or other uses. And we're inviting three-way partnerships with strategic customers and partners to do so. And speaking of error correction, I mentioned this is sort of a big frontier in quantum computing. That particular paper that I mentioned, led by Harvard, was awarded the Physics World Breakthrough of the Year in 2024. And we believe that QuEra and collaborators are truly at the forefront of error correction and error detection. Last, we don't do this alone, although we're exceptionally good at creating quantum computers. There are other areas of quantum where we bring in partners, whether it's in quantum chemistry or training or optimization. We formed what we call the QuEra Quantum Alliance, where we partner with fantastic companies worldwide to go and deliver value together to customers. So with that, maybe Pablo, I can turn it over to you guys, to Pablo and Harry. Maybe you could introduce yourself in a minute and start the meat of this presentation.
Yeah. Hey guys, I'm Pablo. I'm a third-year PhD student at Harvard, working with Misha. And the paper I'll present today, let me share the screen, is a collaboration with QuEra, Chicago, Caltech, and Arizona. And
yeah, and I can give a short intro as well. Yeah, I'm Harry Zhou. Some of you who've been to previous webinars may have seen me in a couple of them. So I work on quantum error correction and related architecture questions at QuEra.
so the paper that we will go through today is at the intersection of these two areas that Eva mentioned at the end, which is error correction and also trying to scale up to the future. And the title is Constant Overhead Fault-tolerant Quantum Computation with Reconfigurable Atom Arrays. So what's the challenge for large-scale quantum computation? The challenge is that the current physical qubits, like the atoms or the superconducting qubits, have error rates of the order of 10 to the power of -3 to 10 to the power of -4. And in order to run large-scale quantum algorithms, we need around 10 to the power of -15, which is over 10 orders of magnitude less error than what we have right now. And it's very unlikely that by engineering better physical qubits, we will ever overcome this gap. So we turn to quantum error correction, which will help us to bridge this gap. In our work, we propose to bridge this gap using a special class of codes known as high-rate quantum low-density parity check codes, of which we'll see an example in a few slides. We provide an implementation blueprint for both storing the logical qubits and also performing gates on the qubits, as shown on the screen, where the logical computation is performed by teleporting the qubit from the dense LDPC memory block to some computing code like a surface code through the use of a mediating Ancilla. We show that in our work, we can achieve order of magnitude qubit savings compared to an architecture based entirely out of surface codes. So for example, what we're plotting here in these phase diagrams is the number of logical qubits on the y-axis required for some computation against the target logical failure rate on the x-axis. And we can see, for example, that at a target failure rate of like 10 to the power of -5, which is where the star is, and 200 logical qubits, the LDPC architecture requires like 2,500 physical qubits, whereas the surface code only architecture requires 10 times more, roughly 50,000 physical qubits. And we will build up to these results now by doing a quick review of error correction and going beyond the surface code. So Recall that an NKD quantum code uses n physical qubits, like your atoms, to encode k logical qubits, each one protected to a distance d, which means that roughly d errors need to occur in order to damage your encoded logical qubit. The rate of the code is the number of encoded logical qubits over the number of physical qubits that we use for the code. An LDPC code, low density parity check code, is one where the checks of the code, which are used to flag errors, are small, meaning that they have constant weight and don't scale with system size. And also the degree of each qubit, which means how many checks the qubit touches, is also bounded and a constant. So technically speaking, the surface code, which people have studied for a long time, is also LDPC because each check is only weight 4. However, we can try to find better codes than the surface code. In particular, good codes are those where the number of encoded logical qubits scale linearly with the system size, and also the distance scales linearly. The surface code only encodes one logical qubit and has square root distance. Because of the fact that it only encodes one logical qubit, the rate of the code, as we scale the size, is asymptotically 0. And as a result, as Litinsky asserts in his paper, schemes based entirely out of surface code for large-scale quantum computation will require a lot of physical qubits. So it turns out that if we restrict ourselves to 2D locality, then there is a bound, the BPT bound, which is stated on the screen. And this bound is actually saturated by the parameters of the surface code. And so if we want to do better than the surface code, we need to look outside of 2D locality. So what are some of these non-local codes? An example of such a code is a hypergraph product code, which I will now explain. So the hypergraph product code is a quantum code constructed from the product of two classical codes. We get two classical codes and we lay one vertically and then we lay the other one horizontally. So here open squares are classical checks and open circles are classical bits. And we draw a connection between a check and a bit if that bit is in the support of the check. Then the quantum code is constructed on a grid where at the intersection of a bit and a bit, we put a qubit. At the intersection of a check and a check, we also put a qubit. And then at the intersection of a bit and a check, we put an X stabilizer for the quantum code. And at the intersection of a check and a bit, we put a Z stabilizer. The connections of the stabilizers for the quantum code are inherited from the connections of the classical code. So if we take the hypergraph product of two repetition codes, we actually get back the surface code. So if we want to find something slightly better than the surface code, we need to look outside of these repetition codes. And an example of classical codes which will yield better quantum parameters are those where the number of encoded logical bits scale linearly with n. And then when we take the product of these codes, we end up with a quantum code where the number of encoded logical qubits scale linearly with n, which yields the constant rate that we want. So how do we construct these classical codes in our results? We use these so-called 3-4 biregular Tanner graphs, which simply means that, so it's just a bipartite graph where we have bits on one side and checks on the other side. And the degree of each bit is 3 and the degree of each check is 4. So these graphs are random and we optimize them for various parameters, including a girth, expansion, and then performance. By constructing this family of classical codes and then taking the product of them, we can construct a family of quantum codes, of which the 3 smallest instances are shown on the screen. And we will be studying these codes in more detail in future slides. So now that we have these codes with non-local connections, we need an architecture that will allow us to implement the non-locality. And a very promising architecture is this neutral atom architecture, where qubits are defined on the hyperfine levels of atoms and are trapped in optical tweezers, which can be moved around. They have long coherence times of the order of seconds, and we can perform single qubit addressable gates through local Raman pulses, which have fidelities greater than 99.9%. And we can also perform 2 qubit gates through the Rydberg blockade mechanism, where we basically shine a global pulse. And if 2 qubits are next to each other, then they will undergo an entangling ZZ gate. And if they're far away from each other, then they will just undergo an identity gate, so they won't entangle. Recently, it was demonstrated that the fidelity of the 2 qubit gate can be brought above 99.5%. These reconfigurable atom arrays provide unique opportunities for error correction. And an example is the recent Nature paper, where I will show one particular experiment from that paper in this slide. So here we create a 4 logical qubit GHZ state using STEAM codes or small color codes. The circuit is as follows. We prepared 10 non-fault tolerant STEAM codes using a depth 3 circuit. We then perform STEAM style error correction through the use of these transversal CNOT gates. We move the Ancilla qubits to storage, away from the decoherence of the global laser. And then on the first 4 logical qubits, we perform the GHZ circuit, which is a transversal Hadamard followed by transversal CNOT gates. So you can see here the 3 steps, 1, 2, and 3, to encode non-fault tolerantly, followed by STEAM style error correction, transversal CNOT, the movement to storage, and then the CNOT gates to create the GHZ state on the first 4 logical qubits. The key point from this slide and looking at this movie of moving all these logical qubits in parallel is that the enabling feature of these atom arrays is the efficient parallel classical control of multiple blocks at the same time. And this becomes very convenient when, for example, trying to implement the product structure of Hypergraph product codes. This is because as we saw before, the structure of the Hypergraph product codes is not completely random. All the qubits in checks, they lie on a grid, and checks connect either horizontally or vertically, and all of the connections are inherited along each of the columns and also along each of the rows. So with this in mind, the way that we can implement the connections or the ZZ gates for the Hypergraph product code is that we can first try to implement the horizontal connections by permuting the columns, then bringing the qubit and check that need to perform an entangling gate next to each other, shining a global pulse, and then so that will implement one horizontal connection, and then we can permute the columns again to implement the remaining horizontal connections. Once those connections are done, we can perform the vertical connections by permuting the rows, which is this figure C here. So, okay, so we know how to implement the syndrome extraction circuit. The only thing that remains is to find an efficient algorithm to permute these rows and columns. And so we came up with this very efficient log depth algorithm to permute the rows and columns. So it goes as follows. Suppose you have L qubits in a line, and then some empty workspace. And then you have some target permutation that you want to implement. Then at each step of the algorithm, you move to the right half, the qubits that in the final target permutation end up in the right half. And then you compactify, and then you repeat the algorithm on each new subhalf. And because you're halving the problem step, the problem size at each step, the scaling of the algorithm is logarithmically with the input size. So with this algorithm, we calculate that the time required to implement a syndrome extraction circuit for the Hypergraph code is orders of magnitude less time than the coherence time of neutral atoms. And also, we made a movie showing this entire algorithm. What's nice about this movie is that it was made using experimental software and commands. So it shouldn't be too much of a hassle to plug it into the experiment and run the actual experiment. So here you can see that we're permuting the columns to implement the horizontal connections. And then the red pulse that you see is a global laser, which shines once we have the qubits that are meant to be next to each other. Okay, so next we assess the error correction performance of the scheme by performing circuit level simulations. And in particular, the simulations that we first perform are memory simulations, where we encode a logical qubit in the state of the LDPC code, and then we repeat multiple rounds of error correction, where within each round, we perform the syndrome extraction circuit for multiple cycles. We decode, and then we apply correction. And then at the very end, we measure the state of the qubit. And then if the measured state, together with the correction, is not equal to the input state, then we call that an error. Otherwise, we say that the error correction succeeded. We will use an important property of Hypergraph codes and other LDPC codes, which is that they satisfy the syndrome confinement, which basically states that qubit errors cannot grow without triggering more measurement syndromes. This syndrome confinement, together with the fact that we have bounded check weight and a special structure of the Hypergraph code, allows us to do single-shot decoding. Single Ancilla syndrome extraction circuit is fault-tolerant and distance-preserving. And yeah, so in our paper, we proved the existence of a threshold under these considerations. So the decoder that we use is belief propagation on all the rounds, except on the final round, where we supplement belief propagation with a slightly better decoder called order statistics decoding, which allows us to bring the state of the code back to the code space and infer the logical state. You can see the result on this slide, where on the y-axis, we're plotting the logical failure rate of the entire block. So if any one qubit of the LDPC block fails, we declare the entire thing a failure. Against the physical error rate, so these are the errors on the gates of the circuit. And we see that under a circuit level depolarizing noise, where we exclude idling errors, we obtain a threshold of 0.6%, which is competitive with this 1% from the surface code. And moreover, when we include idling errors that are realistic and scale with the system size, we see negligible effect on the performance of our scheme. And in particular, this is due to the long coherence times of neutral atoms, which make these idling errors not very harmful. So we find that to account for these idling errors, we can rescale the gate error rate, which is why on this plot, you can see that these points are not vertically aligned, but are slightly shifted. And the greater the code size, the more shift there is. So even after accounting for idling errors, we still observe that below 0.6%, we observe exponential suppression of the error rate. And if we now look below threshold and fit for the subthreshold scaling of the codes, we can reconstruct this phase diagram that we saw on the initial slides, where we have the target number of logical qubits on the y-axis and the target logical failure rate on the x-axis. Together with the Hypergraph product code, we also ran lifted product code simulations. And on this phase diagram, we are plotting so lifted product code is another code which can be derived from the Hypergraph product code. And on this phase diagram, we plot the best resource overhead when considering each of the Hypergraph product and lifted product codes. The start point that we saw at the beginning is from direct numerical simulation of the lifted product code. And we also made a table here of which all the numbers here are from direct numerical simulation. And we have the target number of logical qubits, the target logical failure rate, and then the number of physical qubits required for each of the Hypergraph product and lifted product codes, together with a multiplier showing how much savings we obtain compared to a scheme based entirely out of surface codes. So a few conclusions that we can draw from the table are that LDPC codes start outperforming surface codes at several hundred physical qubits, and all of this is done at a fixed physical error rate of 0.1%. Throughout the entire phase diagram, we observe order of magnitude qubit savings compared to surface codes. And we also see that less than 100,000 qubits are enough for 1,000 logical qubit computation. So that was memory. And now to perform the operations on the encoded qubits, we propose a scheme where we interface the LDPC block with a computational block like a surface code, mediated by this Ancilla block. And we also show that if we operate on a few of these logical qubits in parallel, we can maintain the constant space overhead inherent of this LDPC memory block. Our contribution is a qubit efficient teleportation gadget between LDPC and surface code. And by simulating this, we presented the first numerical simulations of doing computation with LDPC codes. So to understand how to perform this teleportation, let's do a quick review of measurement-based gates. So it turns out that all Clifford gates can be decomposed into single and joint Clifford measurements. So for example, a CNOT gate between the C and T can be broken down into a joint XX measurement, joint ZZ measurement, a single qubit X measurement, and then some feed-forward corrections. To implement this on logical qubits, which is what we're trying to do, we use a trick known as lattice surgery. So to implement these joint logical measurements in lattice surgery, you find two codes with similar boundaries. You identify a logical operator at the boundary, and then you merge the codes so that the joint logical operator becomes a stabilizer of the new code. And then, because we know how to measure stabilizers fault tolerantly, we can measure the stabilizer of the merged code and infer the value of the joint Pauli measurement that we want to perform. And then we split the codes and resume with the computation. So the problem, so teleportation can also be implemented through a measurement-based approach. The problem is that the LDPC block has a very funny boundary given by these Tanner graphs, and the surface code has a repetition code boundary. So direct interfacing between the two is not so straightforward. So this is the solution that we propose. Suppose we have an LDPC block, as shown here, and and we identify a logical X at the boundary, and we identify a logical Z at the boundary of the surface code, we can associate each of the logical operators with classical codes by mapping the qubits incident to the logical operator to classical bits and the checks to classical checks. Once we have these associated classical codes, C1 and C2, we can take the hypergraph product of the two to form the Ancilla block, which is HGP of C1 and C2. Because of the structure of the hypergraph product, the columns of this Ancilla block look exactly like the logical operator of the LDPC block, and the rows of the Ancilla block look exactly like the logical operator of the surface code. And because of this, we can perform direct lattice surgery between boundaries of the same type. This allows us to perform joint XX between LDPC and Ancilla, and joint ZZ between surface and Ancilla. And this is actually all we need to perform the teleportation between the surface code and the LDPC block, where the teleportation circuit, you can see, is shown here, and it only requires this XX measurement, ZZ measurement, some single qubit measurement, and then a feed-forward corrections. So in our paper, we proved that this protocol is fault-tolerant. The fault tolerance of the surface code protocol was already known, but the fault tolerance of this LDPC emerging is what we prove in the paper. And then we go ahead and we simulate this scheme. The main difficulty that we encountered when simulating this scheme is that the LDPC block is single shot, which means that only a single round of error correction is required to be tolerant to measurement errors, as opposed to the conventional D rounds. But the Ancilla and the surface code are not single shot. So when we merge the LDPC block with the Ancilla block and the surface code, the resulting code is not single shot, and so we repeat the syndrome extraction circuit D rounds. And and we simulate noise on this XX surgery between Ancilla and LDPC block. And again, we plot the logical error rate as a function of the physical error rate, where the logical error rate here is for the entire block. So even though we're teleporting a single logical qubit, if any of the logical qubits of the LDPC block fail, we declare the entire thing a failure. So we see that we maintain the high thresholds of 0.6, 0.7% that we saw in memory, and also the low error rates that we saw in that case. Okay, so as an outlook, we explored some LDPC challenges and opportunities on near-term hardware. There's a space-time trade-off. So the LDPC block allows us to do constant space overhead, potentially at the cost of poor time overhead, because we can only operate on so many logical qubits at the same time. This could be okay in various different settings. For example, when you value space resources more than time resources, or when your algorithm is already naturally serial and not parallel. And looking into the future, improving LDPC computation will be important. And there's actually been a lot of really great work that came after we wrote this paper, including doing direct transversal gates on LDPC blocks, and better decoders than this quite slow and memory intensive BPOST, also more efficient lattice surgery protocols, and potentially better codes, such as the BB codes from IBM. So with that, I want to thank all of my collaborators and thank everyone who attended the webinar. Thank you.
Thank you very much, Pablo. Harry, any comments on future directions or things that you would like to emphasize for this work?
I think this was a great summary, yeah. And I think really there's been a lot of exciting work throughout the field thinking about now more and more mature LDPC architectures. So I think there's certainly a lot of exciting follow-up work to do.
Very good. I see a couple of questions from the audience, I think. Let's see if we can. So the first question is, in hypergraph product construction, what's the relation between the classical code used and the boundary in the lattice search array?
So yeah, so when we take, so maybe I can use this image here. So when we take the hypergraph product code, the rows here look exactly like the logical used horizontally. So in this case, the repetition code of the surface code. And the columns look also the same as the code used, the classical code used to construct vertically. And the connections are actually also inherited from each of the classical codes. So there is a direct association between the two.
Wonderful. So I see there are no additional questions. We are going to post this recording. Please join us for future Science with QuEra webinars. Pablo and Harry, thank you very much for the work that you did in this paper, of course, and for the presentation as well.
Thank you.
Thank you very much.
Thank you, everyone. Have a great day.